Hi and welcome to this section where we are going to look at quadratic interpolation. So given 3 points y0 which is equals to f of x0, y1 f of x1 and y2 f of x2, we would like to approximate the curve of the function f between at an intermediate point, okay, passing through between n of these points here on this line here, given these 3 points. So here we approximate them with a parabola. This is here a polynomial of degree 2, okay. So we approximate them with this parabola, this polynomial of degree 2, which passes through all those points x0, x0, y0, x1, y1 and x2, y2. Now the number of methods which we can use, there are 3 actually. We shall talk about 3, but then the third one maybe we shall leave it for another section in the book here. Maybe we will start with the first one here, which we would like to look at. We won't go into the derivation, but the derivation is quite easy to see how it comes about. And this is using Newton's, when we are using Newton's forward differences. So using Newton's forward differences, we are going to use, maybe I can write down the general formula. So we shall say f of x, okay, which we can approximate with a polynomial, nth polynomial degree, okay. We are going to write it as, we shall say y0 plus r times the first forward difference evaluated at x0 plus r into r minus 1 over 2 factorial, the second forward difference evaluated at x0, and so on and so on and so on, up to the last term r into r minus 1 times r minus 2 and so on, up to r minus n plus 1 times the nth forward difference, this one here, divided by n factorial, excuse me, where x, of course we know that it is x0 plus rh, and we know that r is given as x minus x0 divided by h, and this r takes on values between 0 and n, okay. So now that we are interested in using quadratic interpolation, i.e. a polynomial of degree 2, okay, we are simply going to set n is equals to 2. So we say that for n is equals to 2, our Newton's forward difference of order 2, of degree 2, sorry, we shall say that we can approximate our f of x using a polynomial of degree 2, and it is simply y0 if we use n is 2 times the first forward difference plus r into r minus 1, second forward difference over 2 factorial, okay. So yeah, we can look at a simple example here, okay. In this example, we would like to use the values in the table below. We have a table which is given already to us, and we would like to use the values in this table, okay. So in the table we have values of x, and then we have values of y, which is equals to f of x, okay. But in this case we have it as cos of x, and then we have the first forward difference, and then we have the second forward difference. So for x0 we have 0.0, and then we have 1.0000, and from 0.2 we have it as 0.98007, and then for 0.4 we have it as 0.92106. So we know the fast forward difference here, okay, fast forward difference, okay, is simply y1 minus y0, okay. So we have y1 minus y0. I'm just writing this for our sake to remember, but you don't need to write that. You only need to know it is this value minus that value. So I will write down what is already in the text. I hope I didn't check them, but you can always check. Please always ensure that what we are writing here is correct, okay. So this one here is simply y1, sorry, not y1, it is y2 minus y1, okay. So the value here minus the value here, and what do we have? We have negative 0.05901, and then we know that this second forward difference here is simply the fast forward difference at y1 minus the fast forward difference at y0. So it is just this value here minus this value here, and it should give us negative 0.03908, okay. So this is our table, the table we have. Maybe I'll write some of these things down for us to remember. This is our x0, this is our x1, this is our x2, this is our y0, this is our y1, this is our y2. This we have already written, and this is okay. So we can now just begin substituting in here by saying that we can generally write f of x to be equals to y0. Do we have the value of y0? Yes, you have the value of y0, which is 1.00000, okay. Then plus r times the fast forward difference. Do we have the value of r? Yes, we can compute the value of r, because r is given to us as x minus x0 divided by h. So for this problem, maybe I should have written it down. We want to find the value of cos 0.28 using this table here. So our 0.28, where does it lie? It lies here, between this one here. This is 0.28. So this becomes our unknown, our x value, okay. We want to find the value at that point, at that intermediate point, okay. So for our r, which is x minus x0 divided by h, okay, we know that our r is x minus x0 divided by h. So it is going to be equal to, our x is 0.28 minus x0, which is 0.0, divided by h, the step length here, okay. We know it is uniform, which is divided by 0.2. So r is 0.28 divided by 0.2. So this is 0.28 divided by 0.2 times the fast forward difference evaluated at x0. Where is that? This one here, the value you have here. In other words, we have everything else. So this is the r. Then this one here, we know the r, and then we know this second forward difference here also. The value is this one here. We already have it here. So we have everything we need. It's just a matter of plugging in, okay. Just do what? Just plug in all the values here, and then you have yes, you have your f, actually this is f evaluated at 0.28, okay, which we can now get using this here. So you can follow through, and I hope you can be able to understand everything in the text. It should not be hard. If there is any problem, you can always put in the comment section. Remember, all we do is just to use this Newton's forward difference formula. Okay, now then the method 2, which I would like us to talk about here, is a method where we know that we want to use, we know that we are using quadratic what is it, a quadratic interpolation here, i.e. we are using a curve of degree 2 to approximate our function here, our function values here. So what we can do is to write down our equation y or f of x, whatever we want, but we can use y or f of x or whatever we want, in the form of a naught plus a1 times x plus a2 times x squared. Okay, so now we can start by saying y naught is equal to a naught plus a1 times x naught, because we know y naught is simply the value of f evaluated at x naught, so x is x naught, right, plus a2 times x naught squared. Then the other equation we have is also a naught plus a1 x1 plus a2 x1 squared. And then what is y2? y2 is a naught plus a1 times x2 plus a2 times x2 squared. So in here we know the value of y naught, y1 and y2, and we also have the corresponding x's. So in this case we are going to come up with an equation of, it's 3 equations and 3 unknowns. And what are the unknowns? The unknowns are a naught, a1 and a2. So we solve this equation for a1, a naught and a2, and then come and substitute it in here, and then now we can find, we can fit for whatever value of x, e.g. in the previous x was 0.28, we can fit it in here and find its value. Okay, let's see if one or two of you are quite confused. Let us start with y naught. Y naught is this one here. So you simply come and write the first equation is that 1.0000 equals to a naught plus, remember y naught is occurring at x naught, and we are just lucky, it's just a coincidence that x naught is 0. So it's going to make our equation quite easy because the rest is 0. This is a1 times 0 plus a2 times 0. Okay, so yeah, it's pretty much done. So here you come up, the next one is y1. y1 is 0.98007. 0.98007 equals to a naught plus a1 times x, and this, the value of x is 0.2. okay, so we have 0.2 a1 plus, this is 0.2 x1 actually is 0.2, then you square it, that becomes 0.04 a2. okay, then the last one y2, this one here, y2, that is 0.92106. 0.92106 equals to a naught plus what is x2? x2 is 0.4, so we have 0.4 a1 plus 0.4 squared, that is 16. 13 over 100, that is 0.16 A2. Okay, so this is this, you have this equation. Remember, this is 0, so we don't need this. And so we are very lucky that we actually, from the very first equation, we already have the value of A0, which is 1. So you can come here and just substitute. This is 1.0, and then this is 1.0. So now you have actually, now we have reduced this to just solving the simultaneous equation, where the only the unknown remaining is A1 and A2. Okay, so you just solve this simultaneously. Okay, solve this simultaneously to find the value of A1 and to find the value of A2. After finding the value of A1 and A2, we come up and write our general equation, our fitted, we can come and fit our data here with a polynomial of degree 2, which will take on the form A0, which we know, plus A1, which we would have found out, times x, then plus A2, which we also would have found out, times x squared. Therefore, if one wants to find the value of cos of 0.28, so we simply compute f of 0.28, which is A0 plus A1, which we have, times 0.28, then plus A2, which we already have, times 0.28 squared. Okay, these two, the answer you get here and the one which we get here should be close enough. Okay, so the other third method is about talking about the Lagrange. Okay, using the Lagrange polynomial. However, there is a section in the notes which is talking about Lagrange polynomial, so we will leave that method for now and leave it until we find it in that section. So that is it. We have looked at the quadratic interpolation here, and one we have used the Newton's forward difference formula. There is no need to derive it, we won't be minding about that, so we simply use that. And then the other, we can also use, you can form these simultaneous equations, okay, which we can solve for the unknowns. Excuse me. So that is it. In case there is any problem, you can please put it in the comment section, and see you in the next video.